Hi, I am K.A. Shahul Hamid, Professor ECE, Sedu Institute of Technology. In this session, we are going to discuss linear control engineering, a topic, Bode plot, and in particular, we are going to discuss one problem related to Bode plot. First, I will read the problem statement. Sketch Bode plot for the following transfer function and determine the system gain k at gain crossover frequency to be 5 radians per second. And the given transfer function is g of s is equal to 1 k into s square divided by 1 plus 0.2s into 1 plus 0.02s. So we need to solve this problem. First step in solving this problem is we have to first step is we have to substitute s is equal to j omega in this equation. When we are substituting s is equal to j omega, we get g of j omega is equal to k into j omega square divided by 1 plus 0.2 j omega into 1 plus 0.02 j omega. Now we need to find out corner frequencies for this particular system function. So for that we have to take the coefficient of j omega. First thing is 0.02 and the second coefficient is 0.02, 0.2 and 0.02. So we have to take first corner frequency is the smallest frequency and second corner frequency is the highest frequency. So now when we are seeing this 0.2 is the small frequency, that is omega c1 is 1 divided by 0.25 radians per second. So we are considering small frequency as 0 omega c1 and high frequency omega c2 is equal to 1 by 0.02 is equal to 50 radians per second, and 0.1 is related to this one and 0.02 is this related to high frequency. Now we have to find the change in slope at corner frequency. When you are seeing this transfer function, we have three terms. One is j omega square, second term is 1 by 1 plus 0.2 j omega, and another term is 1 by 1 plus 0.02 j omega. So first we have to write these terms in terms of corner frequencies in increasing order. So first we are taking the first term j omega square, and second term is 1 plus 1 divided by 1 plus j 0.2 omega j omega, that is and third term is 1 divided by 1 plus j into 0.02 omega. So next we have to write corner frequency in degree increasing order, that is for j omega square there is no corner frequency. For this term the corner frequency is 5 radians per second, and the next term corner frequency is 50 radians per second. Here we have to first write the slope for each and every term. For example, if you are taking j omega which is in numerator, so for example this one like j omega and something, then for numerator j omega we have to give 20 dB, and if it is in denominator then then we have to give the slope minus 20 dB. So by seeing this, for j omega square, for here we have 2 j omega into j omega, that is j omega into j omega. For each j omega we have to give 20 dB plus 20 dB plus 20 dB. So we give the slope is 40 dB. And when you are seeing this one here, j omega is in denominator. If it is in denominator we have to give minus 20, and here also it is in denominator, so minus 20. Now when you are recording this, we have to change in slope in corner frequency. So first term j omega square, there is no change in corner frequency, so this is nil. And now when we are moving to first corner frequency, there is small change in slope, that is we have to add 40 and minus 20. So we have to simply add, and we have to find the new slope, that is change in slope. So 40 minus 20 is 20 dB plus 20 dB. So this is the new slope, And when we are moving from omega C1 to C2, again there is a change in slope because in omega C1 minus 20 dB slope will be changed, it's changed to plus 20. So when you are going to omega C2, we have to add 20 and minus 20. So 20 minus 20 is 0. So this is actually called a change in slope, which is related to corner frequencies. Now we have to find the magnitude. We have to draw magnitude plot. For that we need more number of points. So what we are doing is we are going to select two frequency. One is low frequency and another one is high frequency. We are going to choose low frequency, that is WL omega L, which is less than the first corner frequency, and high frequency, that is this is omega H, that is greater than omega C2, that is second corner frequency. So randomly we can choose the low and high frequency. In this problem we are choosing low frequency. Omega L is equal to 0.5 radians per second, and high frequency we are choosing 100 radians per second. Now we have to find out the gain of four frequencies, that is low frequency omega C1, that is first corner frequency, second corner frequency, and high frequency. We have to find the gain for plotting magnitude. Okay, so first for that we are going to assume let A is equal to, that is gain A is equal to magnitude of GF j omega in dB. So for that we have to find the corner frequency. So at omega is equal to low frequency, that is omega L, A is equal to, that is the gain is equal to, we have to find in dB. So 20 log magnitude of G of j omega, G of, that is G of j omega, that is 20, this A is equal to magnitude of G of j omega, that is in dB. We have to find 20 log magnitude of G of j omega. So we have to find the gain. You find the gain. So for that we are considering first frequency, the low frequency. So 20 log magnitude of G of j omega, that is we are going to find the first term, that is j omega square. Okay, j omega square. Here magnitude of j omega square is nothing but, when you are taking magnitude, j term will go. So 20 log omega square, which is equal to 20 log, that omega L is 0.5 radians per second. I am just simply substituting omega L value here and finding the gain, that is 20 log 0.5. I am simply substituting the value of omega here, 0.5 the whole square, which is equal to minus 12 dB. So first we have determined the value of gain at low frequency, 0.5 radians per second. Now we are going to find the magnitude, that is gain at omega is equal to omega C1, that is first corner frequency, which is 5 radians per second. So A is equal to 20 log omega square, which is equal to, simply we are going to substitute 5 radian per second, this omega, so 20 log 5 square, and when we're taking log and multiplying with 12 to 20, we get 28 dB. Now when we are moving from first corner frequency to second corner frequency, there is a change in slope recorded in the table 1. So here from first to second, first corner frequency, second corner frequency, we have a change in slope. That change in slope is 20 dB. So that we have to consider. So what we are doing is, at omega is equal to omega C2, that is 50 radians per second, the gain A is equal to slope from omega C1 to C2 into log omega C2 by C1. This is a formula to find out the change in slope. Now plus, in addition to this, plus gain at omega is equal to omega C1. So omega is equal to omega C1, gain is 20, already we have determined 28 dB. This one we have determined. So here slope from omega C1 to C2 is, it is, you have to see the table and write the thing. When you are seeing the table, we get this value is 20 dB, and log omega C1 is 50, and omega C2 is 50, omega C1 is 5, plus gain at omega is equal to omega C1 28. So this plus this one, which is equal to 48 dB. Similarly, we have to find the gain at high frequency. High frequency, omega is equal to omega h, that we have considered as 100 radian per second. For that also we have to use the previous formula. A is equal to slope from omega C2 to omega h into log omega h by omega C2 plus gain at omega is equal to omega C2. This we have determined here. This one is here 48 dB. This one we have to calculate. So slope from omega C2 to omega CH, that is, we have to see the table. So at omega C2, the slope value is 0 dB. So from that, when we are moving to high frequency, the slope is 0 decibel. So we are going to use this one, and so slope from omega C2 to omega h is 0 dB into log omega h is 100 radians per second, and omega C2 is 50 radians per second. So 0 multiplied by anything is already 0, plus gain at omega is equal to omega C2 is 48 dB. So the final value is 48 dB. So these are the values which are going to use to draw magnitude plot. So Bode plot consists of both magnitude as well as phase plot. So we have to find out phase angle for each and every frequency. So we are going to find the phase angle. So we have transfer function, and here we are going to find the phase angle pi. Pi is equal to, so here we have to give 90 degree phase angle, plus 90 degree for j omega, which is in the numerator, and if it is in denominator, then we have to give minus 90 degree. In this case, we have j omega square in numerator, so 90 degree plus 90 degree 180 degree, so this is related to j omega square, and we have 1 by, the second term is 1 by 1 plus j 0.2 omega. Here it is in denominator, so we have to put minus. So minus into minus, and we have to find the phase angle of this first order equation, that is tan inverse of imaginary part by real part. Real part is 1, so the phase angle of this one is tan inverse of imaginary part 0.2 omega divided by 1. So this is the phase angle of the second term. Third term is again, it is also in denominator, so tan inverse of the imaginary part is 0.02 omega. Now we have to find phase angle for different set of frequencies. So we are forming a table, and here we are going to list the frequency and the phase angle. So omega is equal to for 0.5, 1, 5, 10, 50, 100. For that we are going to find the phase angle. So for 0.5 radians per second, we have to substitute 0.5 in this equation. So phase angle equation, and you have to find the value of phase angle. For 0.5, the value is around 174 degree. So degree, phase angle in degree, and for 1, when omega is equal to 1, the value is around 167. For 5, 129 degree, and it's for 10, 105.3, and 50, 50.7 degree. For 100, it is around 29.5 degree. So now we have to draw both magnitude as well as phase plot. This is the Bode plot. Here we have to use similar graph to draw the Bode plot. First we take magnitude plot. We have 4 points, that is for low frequency it is around 0.5, for 0.5 radian, per second minus 12 dB. For 5 radian per second, the point is around 28 dB. For 50 radian, it is around 48 dB. For 100 radians per second, it is again 48 dB. These are the 4 points we are going to draw it. So for that, first we are going to mark the magnitude in dB in left hand side, okay, and a degree in right hand side. So left hand side here depends upon the range of the magnitude, that is minus 12 dB to 48 dB. So we have to give the specification. So I am taking a y-axis, that is one division is 10 dB. For example, I am starting with the 50 dB. The next division is 40 and 30, 20, 20 and 10, 0 and minus 10 and 20, like that. So one division, one unit is 10 dB, something like that I have done, and I have marked, it's very important to mark 0 dB line. So just mark the line at 0 dB. Now we have to, when we are taking degrees, that is degree, right hand side, our range is 174 to 29.5, something 29 or 30 degree. So I'm starting with I'm considering each unit is 20 degrees. So I'm starting with 20, then it is 40, 60, 80, 100, 120, 140, 160, 180. So this is enough for us, okay. Now, so these are related to magnitude and degree. Now we have to take frequency. Now taking frequency range is around 0.5 to 100. So I'm just starting with first point is 0.1. So first unit, so next first point is 0.1. The next division is into 10. So 0.1 into 10 is 1. So next division, this one is again 10. So when you are considering next one, it is 100, 1000, something like that it will go. So here when you are taking, each and every section have different values, okay. So here when you are taking this section starting with 1, so first one is 1 point, this is 2, and second one is this is 2, 3, 4, something like that will go, okay. So we have to exactly find the graph and we see the graph and mark the points. Now first value is 0.5. So this is 0.1 and 0.2, 0.3, 0.4, 0.5. So this is 0.5. So for in 0.5 the magnitude is around 12 dB. So I am taking 10 line, and below that one it's 12. So this is the point, first point. Second one is 5 radians 28 dB. So this is 1 and 1 is here, 1 is here, and 5 is here. So in 5 the magnitude is around 28. So it's below 30 dB. The next line is 28. So this is the 28 dB. Then we have 50 radians. So after 10 the 50 radians will come. So here the amplitude in dB is 48. So 50 dB line, below that the 48 dB. Then the same value is repeated for 100 radians per second. So this one. Now we have to connect all these points using scale. When you are connecting, you have to extend the lines. So from 50 dB to 100 dB you can extend, and similarly this line should also be extended. Now on the right hand side, when you are seeing a phase plot for 0.5, the same 0.5, the phase angle value is 174. 174 here it is 180. So below it's 174. You can mark 174 here, and then 1 radian per second. 1 radians per second is here, and the value is around 167. 167 which should be below 170. So this is around here. Then 5 radians per second. 5 radians per second, the value is around 129. So 129 is above 120 and it's around 130, near 130. So this is the point. So you have to see 140 it is in between 140 and 120. Then fourth one is 10 radians per second. 10 radians per 105. 105 should be in between 100 and 120. It's very close to 100. So this is the point. This one, and for 50 it's 50.7. So here it is 50 and it should be in between 40 and 60, and 50 is center, and this is 50. Then 100 it is around 29. It's around roughly around 30. So it is should be in between 20 and 40. So it is, so you have to connect freehand. In freehand you have to connect all these points for phase plot. Okay, phase plot, and connect it and extend it. So here the plot is over, but in the questions they have given and the gain crossover frequency is 5 reading. Generally, gain crossover frequency means in that frequency gain of the system should be, it should be around, it should be 0 dB. Okay, but when you are seeing this plot, what is happening is at gain crossover frequency, that is omega gc, the value is around 28 dB. So here it's happening because we have assumed that k is equal to 1. When you are seeing the transfer function, there is a term called k. K is equal to 1. So we assumed and we have plotted the magnitude plot. Now we have to change the this plot, that is the first plot, so that the gain crossover frequency is around 0 dB. So we have to bring down this this plot, okay, so that the gain at gain crossover frequency, the gain is around 0. So here when you are seeing this, we need 28 dB. So we have to subtract 28 dB from the first graph. So this graph we have to entirely, each and every point we have to subtract 28 dB. When you are subtracting each and every point by 28 dB, the graph will come down. This graph will come down. So this is the new graph. So this one is the new graph, modified graph. Using that we are going to find the value of new gain. So given gain crossover frequency 5 radians, okay, at 5 radians per second the gain should be 0, but the graph, the gain is 28 dB. So hence every point in the graph should be added with minus 28 dB or subtracted by plus 28 dB. Both are same. Now corrected plot, already we have seen it. Now we are going to find the new gain. So 20 log K is equal to minus 28 dB. Now log K is equal to minus 28 dB by 20, and when you are taking antilog in both sides we get, so K is equal to 10 power minus 28 by 20, which is equal to 0.0398, and this is the new gain for the gain crossover frequency 5 radians per second. Okay, so with this I am concluding the problem. We started with transfer function with unknown gain, and we assume that k is equal to 1, and we have solved the problem. And after that we have modified the graph and found the new gain k is equal to 0.0398. Thank you.